Okay. All right. So this is our second talk of today. Professor David Bolin from Statistics at KAUST is going to deliver his second talk on numerical approximation and Bayesian inference for latent fractional SPDEs. David,
yeah, all right. Thank you. All right. Good morning, everyone. As Raoul said, this will be about, as you can see in the title here, about numerical approximation and inference for fractional stochastic SPDEs. So this will essentially be a collection of some results we have done over the last couple of years, and this is joint work with a number of people. So we have Christine Kirchner from Delft, Mihaly Kovacs from Gothenburg, and Alexandre and Chen from my group here at KAUST. All right, so yes, I'm in statistics, and in statistics, sort of Gaussian processes are really essential, especially in applied and spatial statistics. So common applications would be, say, in geoscience or geostatistics. You might have something like climate data, like you have temperature measurements here, and you might want to do, say, spatial interpolation of these. So then a common model would be to assume that you have these point observations or some noise observations of a latent true field of temperatures, which we assume can be modeled through a Gaussian process. And then the common objectives would be that, first of all, you might want to estimate the parameters in this model. So, for instance, if you have some regression for the mean of the process, you might want to estimate those regression coefficients and any coefficients or parameters you have in the covariance function of the Gaussian process. And finally, then estimate this latent process or use this model for whatever it is that you want to actually use to answer any scientific questions you might want to answer through the statistical model. So one of the most popular choices then, I mean, so if you want to specify this covariance, this Gaussian process, you typically have some model for the mean value through, say, some fixed effects or covariates that might be of importance for the problem. And then you have to specify the correlation structure somehow. And the most popular choice in statistics and machine learning is this so-called Matern covariance function, which you can see here. So this is a covariance function with three parameters. Parameter kappa that controls the correlation range, sigma controls the variance, and this parameter nu in that modified Bessel function k nu determines the differentiability or smoothness of the field. So here you can see two examples of this covariance function and corresponding realizations. So there are some problems with this that are well known. The first one is that computation time for inference typically scales cubically in a number of observations. And the second one is that you often need non-stationary models. So it might not be realistic to assume that you have the same correlation structure throughout space, especially if you model like global climate data. For instance, you might think that the variance, for instance, of the process is varying over, say, depending on if you're over land or over oceans, for example. So these are two problems that we would like to address. And one way of doing this is through this stochastic SPDD approach. So it has been known for a long time, since Peter Whittle's work in the late 50s, early 60s, that if you take this particular Gaussian process, so mean zero Gaussian in a field with a Matern covariance function, it can be viewed as a solution to this fractional stochastic SPDD when viewed on the entire of RD. Right, so this fractional parameter beta there is related to the smoothness parameter, to that equation for beta equal to 2 nu plus d, where d is the dimension of the space. So this was used by Lindgren, Rue, and Lindström about 10 years ago now to essentially address these two problems. So the first thing they did was to propose a computationally efficient approximation of these types of Gaussian processes. So a so-called Gaussian Markov-Random field approximation. So an approximation that has sparsity properties that you can use for efficient inference. And the way they did this was to restrict this equation to a bounded domain, restrict the smoothness parameter to be integer valued, and then essentially using a standard finite element, Galerkian finite element approximation. The second thing they noted is that you can actually use this SPD representation to extend the model. So you can, for instance, define what we mean by a non-stationary Matern model by, for instance, allowing this parameter kappa, say, to be spatially varying. So as long as this SPD is well posed, this will give you a well-posed Gaussian random field. So you don't have to verify, for instance, that you have a valid positive definite covariance function in this case. So that's quite useful because it's indeed very difficult to construct valid non-stationary covariance functions. And the second thing to note is that you can actually use this approach also to define what we mean by Matern fields of more general domains. So if, for instance, if you're on the sphere, on the globe, if you're analyzing global climate data, you might want to construct a Gaussian process that's used the metric on the manifold where you have the data. So you can do that simply by posing this stochastic PD on the sphere, for instance. Right. So because of these advantages, this has become highly popular in spatial statistics over the last 10 years. Now, so when we started working on what I'm talking about today, the problem we wanted to address was this restriction of an integer smoothness parameter, and further that there was no formal error analysis available for this finite element method. So if we want to do some kind of error analysis, we would like to do this, or if we want to remove this restriction of fractional smoothness, we would like to do this in the general setting of also allowing for non-stationary models. So if you look in the literature, there has been a number of non-stationary PD-based extensions of these Matern fields that have been proposed. And essentially all of them can be viewed as special cases of what we refer to as these generalized Whittle-Matern fields. So this is random fields posed on some, say, some bounded domain D in RD that are specified through this elliptic equation where you have this second order differential operator, kappa squared minus this class type operator. And for the purpose of this talk, we made the following assumptions then on the parameters of this model. So we assume that kappa is a smooth function, and A is it's a matrix valued function that is symmetric, uniformly positive definite over the domain, and in addition, the entries in this matrix valued function are assumed to be smooth functions. So this is essentially, so these assumptions can be greatly relaxed. So you don't actually, for most of what I've been talking about today, you don't need this smoothness. You can reduce kappa to just be bounded, and A can be assumed to be Lipschitz, for instance. And most of what I've been will be mentioning today we'll go through anyway. But to keep things simple, this is the assumption that we assume here. And we will further then assume, as we stated up there, that we also have a smooth boundary on the domain that we are at. Okay, so if you look at this model, this is actually a very flexible model for constructing spatial Gaussian processes. If you look a bit at what these parameters then are doing, you can note that, so first of all, you have this fractional power beta, where we, by the way, we interpret this fractional power in the spectral sense. So this smoothness parameter is what controls the smoothness of the solution. You can show that we have solutions which are in L2 as long as beta is greater than d over 4. D again was the dimension. And you can also show that if you further increase the value of beta, you will gain kind of Hölder regularity of the sample paths. And then we have the parameters kappa and A, and they essentially controls everything else. So local marginal variances, local correlation ranges, and local anisotropies. So you can see in the figure here to the left, you have an example of this where I just vary kappa over the domain, and to the right you see a simulation where you kind of see that you seem to have longer correlation ranges to the left compared to the right. Sure. So here we're just saying that we have Dirichlet, a homogeneous Dirichlet on the boundary. Again, this is, you can also do Neumann. Then you just have to assume that kappa is bounded from below as well. Yes, exactly. Right. So you will have, I mean, so when you look at this solution, it will not be stationary, right? So as you're right, I mean, for instance, the marginal variances will go to 0 at the boundary. Now, the effect of that essentially depends on kappa. So essentially, if you have, if you look at the field away from the boundary, it will essentially look like the Matern field. So yeah, you extend the domain exactly, and the kind of the error kind of compared to the true, if you just look at the stationary parameter case here, the error between kind of the Matern covariance and the covariance of this will essentially decrease exponentially away from the boundary. So you can extend kind of by something like the rule of thumb would be to extend by kind of 2 times the practical correlation range away from where you have data where you're interested in this. Yeah, thank you. Any other questions? Okay, so before then, we actually go through the numerical methods. Some interesting questions here are, well, first of all, since this is a very flexible model, can you estimate the parameters of this model consistently? And secondly, if you use this model for, say, spatial prediction as the problem I first mentioned, which parameters are actually important for spatial prediction? So do you need the full flexibility of this model if you want to kind of have accurate predictions? So we will focus now for a bit. So we will now for a moment set this particular equation aside and look at this second question a bit in more detail. So the goal now will be to look at this problem of so-called Kriging prediction, and then to see, in the end, we want to kind of understand which parameters here are actually important for prediction. So we can kind of set that generalized Whittle-Matern fields aside for a bit, and just now look at more general problems. So assume that you just have some Gaussian-Reynolds field Z on some say compact metric space, might be the globe or a compact subset of RD, like the domain for our Whittle-Matern field. And suppose that you have some observations of this Gaussian process and you want to predict the value of this process at some unobserved location. So we can call it unobserved location X star, and we have observations at locations X1 to Xn. So I mentioned before Kriging. So Kriging is just linear prediction. So it's a linear predictor of this. So it's our prediction of the process at this unobserved location is a linear combination of the data where we choose the coefficients so that we minimize the variance of the error of the prediction. So this is very popular in applications because it is easy to compute, because it's only if you know the mean value function and the covariance function of the Gaussian process, well, this is then the closed form expression for that Kriging predictor. Right, so this L2 optimal prediction only depends on the mean and covariance function. So the question now is, suppose that you don't know, I mean, which you typically don't, so you don't know the mean and covariance. You typically have to estimate this from data before you do the prediction. So if you do that, it's reasonable to assume that both of these functions might actually be misspecified when you do this prediction. Or if you have, say, the true data is non-stationary, but you assume a stationary Gaussian nanofield model when you do this prediction, then again, you might be using the wrong mean and covariance function when doing the prediction. So what we're interested in then is, can we say something about the accuracy of this prediction if you use the wrong second order structure, M-row? So to do that in general is quite difficult, but we can say something asymptotically. So what we will be interested in is essentially the asymptotic behavior of the error of the Kriging predictor based on the misspecified mean and covariance compared to the optimal error as the number of observations go to infinity. Right, so this is something that we're interested in order to understand essentially which parameters of these Whittle-Matern fields that are of importance. So the goal now would be to obtain conditions on this second order structure that would guarantee asymptotic optimality of linear prediction, and we want this to be uniform over the prediction locations. So we don't want to fix this point x star in just one of them, but we would like this somehow to hold uniformly for all possible predictions you might want to do. Right, so the setup then is the following. So as I said, we assume that we have a Gaussian process on some compact metric space curly x. We call the Gaussian nanofield Z. We assume that this is square integrable. It has a covariance, has a mean value function in L2, and a strictly positive definite and continuous covariance function rho. So based on that, then, so if you have the covariance function, you can define the corresponding covariance operator from L2 to L2, which is self-adjoint, positive definite, and compact. And then finally, based on this Gaussian process, you can introduce the corresponding Gaussian measure. So the Gaussian measure that is induced by this Gaussian process, it is simply the measure that for any, say, Borel set A, the measure of this set is given by the probability that this Gaussian process takes values in that set. Right, so this is some notation that we need for the Gaussian process. So then let's formalize what we mean by this Kriging sort of the mathematical setup now for studying this Kriging problem. So to keep things simple, let's assume that the Gaussian process is centered. So we have mean zero, just to simplify the notation a bit. So what we then typically do is that we can introduce a vector space of all of linear combinations of point observations of this Gaussian process. So these are then the type of things that we would use. All Kriging predictors would be of this form. And then you can define a Hilbert space by taking the closure of this vector space under the L2 inner product. So then you get something that we call curly H. This is a Hilbert space with the L2 inner product. And that essentially contains all elements that you might be interested in predicting. So it might be point observations, it might be linear combinations, or it might be something like integrals of the Gaussian process. If you want to estimate like the mean of the process over a domain, then that would be basically a limit of such a thing. Right, so now we want to predict an element in curly H, and the Kriging predictor, Hn, based on some set of observations, that is nothing else than the orthogonal projection of the element that we want to predict onto the span of these observations. So this is kind of why we have this variance optimality property of the Kriging predictor. Now, if you look at that, you can then see that the Kriging predictor, for any age that you want to predict, the Kriging predictor is actually fully determined by this subspace curly hn, which is the span of the observations. So because of that we can either say that we have the Kriging predictor based on the observations or based on this space curly hn. That's saying the same thing two different ways. Right. So again, the main question now is what happens if you, instead of the optimal Kriging predictor, use a linear predictor that we called HM tilde, that would be the Kriging predictor if this Gaussian measure mu tilde based on the misspecified second order structure was the correct model. So then to answer that, we have to say something about, so we want to look at this asymptotically, so we need to say something about how do we get the data. And the only thing that we will assume about the data is that we get the observations so that we get consistent Kriging. So basically, we assume that when you get more data, the mean squared error goes to 0. So that simply means that you cannot take all observations at one point, because then you kind of then you wouldn't get kind of more information if you get more observations. So that is essentially an assumption on how you observe your Gaussian process. So then you can introduce this set S mu basically on all admissible sequences of observations that you can take in order to get consistent Kriging prediction. So for instance, if you have everything based on point predictions here, then you could note that any sequence Hn would be admissible if essentially you have that for any point in the space that where you are, you have observation locations that are accumulating at that point. So essentially, for any point that you might want to predict, you can have, as the number of observations goes to infinity, you will have as many observations as you want in a small neighborhood around that point. Okay, so this is the setup, and then now we want to say something about them. So what can we say about the quality of these misspecified Kriging predictors? So it is well known, actually. So it has been known already since the late 80s, early 90s, where Michael Stein showed that you obtain asymptotically optimal linear prediction if the Gaussian measure based on a misspecified covariance structure is equivalent to the true Gaussian measure. So meaning that they agree on which Borel sets that are null sets. Right, so this was a nice result by Michael Stein, published here. Well, first in this 90s paper, he showed that you have actually uniform asymptotic optimality if that holds. So the question is then, when does it hold? And that is given by this famous Feldman-Hajic theorem that gives you necessary and sufficient conditions for when two Gaussian measures are equivalent. So the Feldman-Hajic theorem says that so the Gaussian measures would be equivalent if these following three conditions hold. So the two Cameron-Martin spaces corresponding to the two covariance operators are isomorphic. The difference between the mean fairly functions is smooth enough, meaning that the difference should be in that Cameron-Martin space. And finally, we have this kind of most technical assumption that says that this operator T1 that involves the true covariance operator and the misspecified one, if you take this thing minus the identity, this should be Hilbert-Schmidt on L2. So under these conditions, so if you would have a misspecified second order structure so that these three hold, then by the result by Michael Stein, we know that you have uniform asymptotic optimality. Now, the problem is that these are sufficient, but they are far from necessary. It's very easy to come up with a counterexample where you would have uniform asymptotic optimality without these conditions holding. And the simplest case is actually to just take C tilde as a constant times C, because then this can never be Hilbert-Schmidt. But if you just misspecify the covariance function of mu tilde by a constant, that actually doesn't change the Kriging predictor. So it's actually equal to the optimal one. So that's kind of a nice counterexample that shows that these are too restrictive for if we want to look at this Kriging problem. What we instead came up with are the following assumptions. So our Kriging assumptions that we will show are necessary and sufficient for this Kriging problem. So we assume that we have, so the setup is exactly as before. We have our two covariance functions. We have our two mean value functions, and then we assume these three things. We can note that the first two assumptions here are the same as those in the Feldman-Hayek theorem. So the only difference is the third one that says something about this operator that we call TA. And if you look at that, you can see that this is basically like our operator T1 here, except that you have a coefficient A there. And the assumption then is that this operator TA is compact. So there is an A, there is a constant A positive, so that this operator is compact. And since every Hilbert-Schmidt operator is compact, this kind of then shows that this holds in greater generality than the Feldman-Hayek theorem. So under those three conditions, we have the following results. That says that, so if you are again in the setting, we have our correct Gaussian process, we have our misspecified one, and then we have the optimal Kriging predictor and the Kriging predictor based on a misspecified one. Then we have, in particular, this first result. So this is this uniform, this premium there, this uniformity, asymptotic optimality of the misspecified Kriging predictor, or any of these other three similar results. So this basically says the following thing for if you change the order of mu and mu tilde. This holds if and only if these three conditions, the Kriging conditions, are fulfilled. Right, so that's the result. And these two last things here, they basically say that if you evaluate the error of your Kriging predictor using the wrong model, so you compute the expectation here under the wrong model, then this has to be bounded. And so this compared to the true error, the error under the wrong model is bounded. And so this minus A should go to 0, and that A is exactly that A there. Okay, so this is the result. So these are essentially what we can say about Kriging prediction. So basically, to check if you have sort of what's important for Kriging prediction, you essentially have to check these three conditions. So the problem then is, of course, that these are conditions formulated in terms of the covariance operator of the Gaussian measures, which in general is quite difficult to look at. So and it might not be trivial to check if this operator is compact. Fortunately, for this, now going back to the Whittle-Matern fields, in that case, we can actually do that. So if we now go back to the specific setting that I started with, so we go back to this fractional stochastic PD, and then we look at the Gaussian measure mu corresponding to the Gaussian process induced by this stochastic PD, and mu tilde is the Gaussian measure, well, for this PD, but with different parameters, beta tilde, A tilde, and kappa tilde. So then we have the following table here that essentially summarizes the conditions on the parameters in order to get either asymptotically optimal linear prediction or equivalence of Gaussian measures in dimensions 3 or dimension 4. The details here are not so important. So some broad things that you can note is that, so as I said, equivalence of measures requires more than asymptotic optimality of kriging. You can note that if you want equivalence of measures in dimension d greater than or equal to 4, you need all parameters to be equal. But if you go down to, say, asymptotic optimality of kriging, it depends a bit on what the parameter beta is. But what you can note is that, well, for instance, in this case here, there is no requirement on kappa. So that parameter kappa actually asymptotically doesn't matter for the quality of the linear prediction. Another thing that you can note is that for all of these results, you must have that beta is equal to beta tilde. So no matter if you want to do prediction or if you're looking at equivalence of Gaussian measures, which is also needed, for instance, if you look at say, do parameter estimation, then typically you have to use equivalence of Gaussian measures if you want to study asymptotic behaviors, for instance, of maximum likelihood estimators. Well, then we see that this fractional smoothness parameter is really crucial. Right, so this really serves as a motivation that we really want to be able to allow for a general fractional smoothness parameter beta. So that was so this is kind of a motivation for why we want to remove this restriction in the original SPD approach. So basically, because what I just showed, that beta is crucial for the accuracy of kriging, but also, I mean, if you keep beta fixed like this, you can, for instance, not allow for an exponential covariance in R2. Right, so this is now the goal. We would like to come up with a practical method that generalizes this SPD approach to arbitrary smoothness. So as I mentioned, the main idea for the computational method of this SPD approach was to do a finite element discretization. So that we will do as well, also in the fractional case. So we do just a standard Galerkin finite element approximation. So we take our domain, we take some mesh over the domain, and then based on this mesh, we introduce just a family of standard continuous piecewise linear basis functions based on that mesh. And based on that, you can then discretize the SPD in a standard way, as you would for any elliptic PD. So then you would arrive at this discretized equation, where importantly, if you want to sample this, you have to sample the load vector, which so WH here, that is Gaussian white noise in our finite dimensional space VH. And an important note here is that this has a known distribution. So the load vector you have to sample is just a multivariate normal, where the covariance matrix is equal to the mass matrix of the finite element basis.
Can I ask you a question?
Yes.
So you said beta there is larger than b divided by 4, right?
Yeah.
So and why do you then take the VH just including H1? Couldn't you need more regularity out of this VH space?
Right. So it might be, yeah, that's a good point. So I will show you basically the regularity results for piecewise linear finite elements, but you're right that if you increase beta here, at some point it might be meaningful to also go to higher polynomial finite elements. Yes, that's right. But yeah, so I mean, basically to keep things simple, we will just do it with this piecewise linear here. And also that is kind of what is usually done in this SPD approach. Now, so the main problem here is that if beta here is not an integer, then you have to handle this fractional power somehow, right? So that is what we have to handle now. And the idea we had was that we could try to construct an approximation that is of this form. So here, so this is again in our finite dimensional space VH, but instead of looking at this equation, we have this fractional operator. we look at this equation where PL and PR are just two polynomials evaluated in our operator LH. So since these are polynomials, they are commutative by construction. So because of this, you can rewrite that as a system of two equations, where this is then a standard non-fractional elliptic PD. So this is basically by this standard SPD approach, this would give you a Gaussian-Markov field approximation. So essentially, this is a latent GMRF. So because of that, you can basically use all computational methods that we have for Gaussian-Markov fields in statistics. So if you can find these two polynomials, then you could use this method for basically statistical inference in the same way as you would for the non-fractional case. So the question then is, well, how do you find these polynomials? How can you make sure that this is a good approximation? And so there are many ways that you can actually do this in. So one idea that we had was that you can compute this, so the coefficients in these polynomials, simply by doing a rational approximation of that real-valued function x to the power of beta. So you do a rational approximation of that real-valued functions, and you use the coefficients in that rational approximation when you evaluate these polynomials here. So if you do that on some interval that covers the spectrum of the inverse of the differential operator, so since I mean, we assume that that is complex, so this is how the spectrum is a bounded interval. So you can do this this rational approximation on some bounded interval of that function just to get the coefficients. If you want to get if you want to maintain some kind of smoothness properties, we actually don't do that. But what we instead do is that we get basically out the smoothness parameter n beta, which essentially is the floor of beta. We decompose this function x to the power of beta in this way, and you do the rational approximation of essentially the remainder, so x to the power of beta minus n beta. Okay, so if this is how we compute the coefficients, and if you compute then this rational approximation in the L infinity best way, so this can, for instance, be done using the so-called Remé algorithm, then we can get explicit rate of convergence for strong errors of the difference between the true generalized Whittle-Matern field and this rational approximation. And you can also get explicit convergence rates for the weak error, which essentially is doubled compared to the strong rate as usual for these types of results. And the crucial thing here is that so these rates are given in terms of the mesh width of the finite element mesh, and this m, so this is the order of the rational approximation. We know how we can calibrate that with the finite element mesh width, and essentially this is calibrated as log of h. So this rational approximation is exponentially convergent, so essentially you only need a few terms there to get a good approximation. Okay, so just going back to the inference part, so assume that you would use this approximation for statistical inference in this simple statistical model that I started with. So where you just assume that you have some noisy point observations of the Gaussian process, which we approximate now using this rational approach. Then if you do the finite element discretization, then essentially this becomes just a system of multivariate normals, where essentially all matrices here are sparse. So that's why you can use them the efficient methods for actually doing computations with this. So now, if you only want to do sampling, like Monte Carlo sampling here, this works beautifully. The problem is that in statistics, sampling is kind of, in some sense, trivial. The difficult part is doing inference. So if you want to do, say, likelihood inference, you have to work with something like, for instance, this posterior precision matrix that looks like that. And if you look at that, this is basically has the same sparsity structure as the mass matrix to some power 2 times, and then here's the order of the rational approximation. That means that this quickly becomes non-sparse as you increase the order of the rational approximation. And worse, it quickly becomes ill-conditioned numerically, essentially because this is kind of like the condition number here will basically work like the condition number of the stiffness matrix to some power. Right? So if you want to do inference, you actually must have a quite small value of m here for this to be numerically stable. So that has been a bit annoying, and we have been thinking about ways of getting around this. And one way of getting around it is to actually realize that we don't really care so much in statistics about pathwise convergence like here. You don't really care so much about the strong error because for statistical inference, you're mostly interested in approximating the distribution. Right? So because of that, what you might do instead, instead of trying to target approximating the solution U explicitly, you might want to simply just try to approximate the covariance of the solution. So what we can do is do exactly the same type of rational approximation, but instead of doing it for the differential operator, we do it for the covariance operator, which is then L to the power of -2 beta. So this gives us two things. The first thing is that it actually will increase the accuracy of kind of for given computational cost, will gain in accuracy of the covariance approximation. It also enables a representation in terms of the approximation then as a sum of Gaussian-Markov fields. And this actually will be quite beneficial for doing more numerically stable numerical inference or statistical inference. All right, so if you compute these polynomials in the same way, you do the rational approximation by computing rational approximation of this function to get the coefficients. Then we have the following result here that shows the rate of convergence now for the covariance function. So this is just showing the L2 norm of the difference between the true generalized Whittle-Matern covariance function and the rational approximation of it. And again, it is bounded in terms of the mesh width. And if you calibrate the order of the rational approximation with the mesh width, you get this rate of convergence. Right. So this basically shows that we have some control over the accuracy of this method. So again, as I said, if you now do use this type of rational approximation for statistical inference in the same model again, as I said, you can then write the approximation as a sum of Gaussian-Markov field. So then, if you do the finite element discretization, you would get a system like this here. And now, importantly, the latent field X here, it is of higher dimension, but essentially the sparsity structure is the same. So now you are not losing as much in the kind of condition numbers as you did before. So this will be a lot more numerically stable. And also importantly, this representation now allows us to implement these models in R-inla. So I guess you heard about Håvard Rue talking about in his talk yesterday. So R-inla or inla is a very popular method and R package for doing computationally efficient Bayesian inference of latent Gaussian models. Essentially of these forms, you have some kind of likelihood distribution, and then we have the latent process of interest, which we assume is a Gaussian-Markov field, and then we might have some priors on the coefficients. And this framework here, this operator-based rational approximation that we started with, doesn't really fit into this framework, but this covariance-based approach does. So just briefly, we have implemented this in this inla package. So there is now support for these fully fractional models in our inla. So I think I'm skipping some. So here's just some some results or some comments on the implementations that you can do. So maybe it's easiest actually just show the code directly. So here's just an illustration. Just some simple precipitation data that you might want to do kriging for. So just to show you kind of the simplicity of the code here. So this is our code for just plotting the data first and then constructing the finite element mesh that we need. So here's the mesh that we use for this particular illustration. And then here is all of the code for actually fitting this model to the data. So we construct this observation matrix that maps between the mesh nodes and the observation nodes. We construct the fractional SPD model. We organize the data, and then we use inlet to fit the results. Right, and here you have then some summary of the outputs. You get these are the posterior distributions for all the parameters, including this fractional smoothness, which you can see. You can see it here. It's about 0.5, so it seems like this fractional smoothness is actually needed in this case. So yeah, that is serves as a motivation for why this might be useful. Right, and finally, then here are just the actual estimates of the latent field. So here is the posterior mean, the kriging prediction, posterior mean, and here are the posterior marginal standard deviations of that estimation. All right, so that was about it. So basically, in summary, formulating these Gaussian random fields via this SPD approach, it's highly beneficial because it facilitates basically easy constructions of non-stationary models. We can do generalizations to models on manifolds, and you can also do generalizations to non-Gaussian models easily, essentially by replacing the Gaussian noise with some non-Gaussian noise. By now, we understand the theoretical properties of these generalized Whittle-Matern fields quite well. And what we in particular know is that if you want to do kriging, this allowing for this fractional smoothness is really important. So we have implemented this rational SPD approach in an R package that, in combination with INLA, can be used. And in particular, we know the theoretical properties also of this numerical scheme. And the implementation then basically facilitates people using these models without so much expert knowledge. So as you saw, the code for actually using this was quite simple. So if you want details here, you have so here's a GitHub page with some various examples of vignettes for this R package that you can try out if you want to. Current work of this includes, for instance, extensions of this approach to space-time models and also models to things like metric graphs, something that we're currently working on. Here are the references of the main results that I've been talking about today, and that was it. Thank you.
Thank you very much. Please.
Quick question. Can this beta parameter be spatially varied?
That's a very good question. Not so. That is something that we really would like to look into. In the current implementation, no. And I mean, basically, the theory that you would need to analyze that would be completely different. Right. Yeah. Okay. So that's a very, it's a much more challenging problem, I would say.
More questions, comments? I mean, I have a similar question about the non-stationarity, right? How do you use maybe this and maybe a small transformation in between to try to adjust to some non-stationary behavior that you expect? I mean, use this stationary field to get some other more general photon dependence.
I mean, basically how we model the non-stationary parameters. Mm-hmm. Yeah, so I guess that is very much dependent on the application. So where do you have a model? So typically what you would do is to do some kind of basis expansions of these kappa and A, so some kind of low rank basis expansions. And then essentially, I mean, you could use basically anything here, but if you want to fit this to data, you need typically something that is low rank so that you can estimate the coefficients easily. So yeah, that's usually what we do.
Okay, thank you. Right. If there are no more questions, then we're checking online too. If there are no more questions, there are no questions online either. So we can thank, and this is the end of the first session today. Thank you so much.